My name is Dr. Migaev, based out of Kiev, from EPAM.
My name is Bertrand Marquis. I'm from ARM.
I'm Stefano Stabellini, and I work for Xilinx.
Today we'll talk about functional safety for generic open source projects on a Xen example. I'll start quickly with background. So what is a functional safety overall? Functional safety in general, if you go through all of the definitions of it, is absence of unreasonable risks for both internal and external hazards, like potential source of harm that can cause malfunction behavior of a system so that outputs are not going to be same as expected, depending on their inputs. And all of that very complex definition is regulated by different standards across the industry. So regulated by different standards, like 61508 is a very generic umbrella standard for all of the industries, saying some definitions. With ISO 262, for example, is application of functional safety regulations for automotive, and MISRA is a very generic coding guidelines and rules for automotive industry that existed even before the previous two appeared, creating deterministic behavior in defensive programming techniques. And these regulations usually demand that product safety requirements are fully defined, and the product team is able to demonstrate that these requirements are implemented properly on every level of the software design. And the requirements, architecture, unit design, and testing, they all comply to best practices defined by the standard regulations. And development process complies with regulations, and all of the processes are strictly followed. So it's all about following very narrowly set definitions. With all that, can actually generic FOSS project be used for functional safety? There are lots of gaps. Like traditionally, FOSS projects lack determinism and fault processing, and there are not much defensive development put in place, although this is changing recently. Certain engineering practices like maintaining very well-defined documentation is not very used in FOSS projects, although it improves in some of them. And strictly following the engineering process, except probably the commit, is also not very well followed. And of course, open source projects do not often use non-free tools, infrastructure, and expertise. So with that, there might be significant changes in how FOSS projects work and manage if they want to be applied for FUSA. And until recently, by industry, it was assumed that these kind of not can be compliant, so FOSS cannot be used in functional safety. Well, at Xen project, we think that is possible. And there are, of course, the catch. So it's extremely hard to follow all of the requirements, and actually tailoring of these requirements is possible, allowed in practice. So that's what we want to do. Of course, the more you tailor, the higher the risk that safety cases will not pass. So the cost will be higher. And tailoring also means that you need to fund a specialist consultancy for assessing company that will help you passing through the gates of certification. And in the end, verification of a product will demonstrate that everything has been done correctly. Or with the help of the specialists, you'll be able to argue that everything is done as good as it can be within the specific standard inquiries. So all of that can be done basically only if assessors are actively involved in development process, which is traditionally not the true for FOSS projects. So for existing projects like Xen, what we need to do, we need to rework somewhat code base to have very well-defined interfaces, modularity, reduce complexity, improve determinism, add fault processing, and improve fault tolerance in general. We need to add all of the missing documentation artifacts like specification, testing. We need to have full traceability between test cases, between code, between documents, which is also very hard to implement. A strictly defined development process, or explain existing development process, find gaps and close these gaps. And after all of that is done, we need to ensure the safety processes rigorously. And the approach we took is we analyzed the previous work that has been done in Xen. Actually, Xen was already certified sometimes for aerospace for DO-178 standard, LC level. And the effort, as we learned it from a company that did it, was like 5 to 15 million years, depending on the code base. And that was needed for one-off certification. That was not done for mainline, for mainstream. That was done for safety, by safety-trained engineers. And the effort actually heavily depends on the code size. So if you look at Xen, like more than half of Xen code is actually x86 part, and only like 25% is a common code, and around 15% is ARM implementation. So it makes total sense to minimize the code base that we want to certify, and that's what we also plan to do. Comparing to what community does in average year of Xen contributions, is the safety certification, like it was done before. It's not too bad. Like we had 30 man years. I think it was 2019 year, and it is much higher than can be needed for minimal Xen. So if you just throw out the x86, keep only common and ARM code, we get around 50,000 lines of code that is compared on par, with the 5 man years, not 1 month, 1 year estimation. But even if you do that, can functional safety be maintained in somewhat adopted FOSS model? To understand that and go into that, we created a special interest group in Xen project. We understood it's going to be a long-term community work. So with leaders for this work being ARM, EPAM, and Xilinx, like where 3 of us are coming from. We have assessors on board like me, Retuf, and Exida, so they help us, and some assessors from ARM as well. Xen project leadership team helps us, and Kate Stewart from Linux Foundation works with us as observer, because there are other Linux Foundation projects going on that are related to functional safety. And of course, we do have some industry representatives who would like to use Xen for the safety applications. So we've made some high-level agreements. So there must be a very clear benefit for the non-functional safety community of Xen. So that's why we need to have some split development model with an open source and closed part. I'll talk about it later. There shall be no uncertainty on why some changes are needed, like, for example, MISRA changes, why they're pushed and why they're needed and how the community can benefit from that. We don't want to change a lot or at all the open development workflow, and everything shall remain Git-centric, and there shall be no fork or parallel universe on the source part. Anything that we do for safety shall be done only if there is an agreement to implement all the changes in the common code. So we cannot do it ourselves. There must be a community alignment if we want to proceed with any kind of changes. So as you probably can imagine, there must be an accountability for the safety case. So we agreed that accountability will not go for a community. Community cannot be accountable for the safety compliance of the project. So there must be commercial vendors. So that's why we probably may have a split development model when commercial vendors use a baseline to sell that act as a accountable part. And there must be maybe some reference text from different companies for safety use cases. We partner with other safety projects in Linux Foundation. For example, with Elisa, we look through the process and so on. And with Zephyr, that will cover later on. We talk about documentation and how to establish a whole process for the safety in open source. And we defined the work scope. We decided to proceed with the ISO 26262 safety element out of context. So that means that Xen itself is not a product, but can be applied as a part of some safety regulated product. And the level of safety we plan to address is ASIL-B. It's not the lowest, but not the highest, of course, level. And our work scope is to identify and eliminate gaps in requirements and documentation, in validation, verification, or testing otherwise. Establish infrastructure for maintenance of documenting and tracing and testing the documents. Implement fault processing, or let's say improve the fault processing and improve the deterministic behavior of Xen. Maybe add some defensive programming, like probably applying MISRA and so on. Not everywhere to reduce code churn, we will have to waste against some of these that are not applicable. We need to support safety certified tools, like, for example, compiler, and have safety management processes and tools in place to ensure that we keep on with the safety process demanded by the regulations. So now to requirements and documentation.
So a big part of the certification process is to write requirements. Next. So how do we develop? We do follow, without knowing it, part of the V model. We start from an idea or a need. This is more or less an high-level requirement. Then we code. Then we push our code to a versioning system like Git. We have to explain it in a commit message. This is a very light, low-level design. Then we use what we did, or we write some tests to validate it. All these steps are parts of the V model. Next. The V model is the same with some more steps. First is high-level specification. Using only those, someone should be able to develop acceptance tests. Then the system specification, which goes a bit more in details. Then high-level design, then low-level design, and finally coding. So we have three groups: the code, requirements at different levels, and different types of tests. Each of these might be done by different people. From experience, far more time is spent on the requirements and tests than on coding. This is where the major cost of certification are. So what is a requirement? A requirement is something describing a single function or feature that is testable, measurable, and expressed in a clear way. Let's see some example. So Xen shall never crash. It's very clear, not ambiguous, but it is impossible to test. Xen shall support up to 64 cores. Easy to test that 1, 2, and up to 64 cores are supported, but not 65. Way to express it is clear and not ambiguous. The way of expression, though, is not really documentation, but the information is there. Xen support up to 64 cores is what you would expect as documentation. But if we choose some clear wording, we could in fact write a requirement this way. Next. One of the big parts of the certification is linking. The goal is to be able to go from one element to all other elements related to it, from the code to the test, from a requirement to the code or the design. It is a very complex and time-consuming task to create those links. The next work is very dense, as not all relations are one-to-one, but many times one-to-one. This is also the first one checked by any certification authority. They take examples and check the root and the consistency. They are very good to know where to hit to find issues. Next. So where to put requirements? Usually you use a proprietary software like Doors from IBM to store them. It's a kind of 3D Excel tables with links. Those kind of products would be very hard to use in an open source project. They are expensive, they require some strong knowledge, and developer would not maintain the database when developing. So we took a strategy compatible with Git and mailing list instead. High-level requirements will be stored in a text file or table, and the rest will be stored directly in the code. We will use Doxygen to extract the requirements. This will allow easier maintenance by developers. Next. So, part of our work is done with Zephyr project. So Zephyr project has already done some investigation and did a proof of concept using Doxygen. We would like to use the same strategy and tools on both projects. We have regular sync with the Zephyr team. We will move Xen documentation to use Doxygen. This is an opportunity to improve Xen documentation and is a preparation for the requirement extraction. And we also started to write some requirements to agree on the terminology and also to have some examples to develop the Doxygen toolings. Stefano?
Yeah, and MISRA-C. MISRA-C is a set of guidelines to write safe software in the C language. It's divided into rules and directives. Rules are things that can be checked just looking at the source code, while directives are a bit more up to interpretation, and they involve also analysis of documentation and the whole process. Rules and directives together, they are divided into three groups that are three categories: mandatory, required, and advisory. Mandatory are rules and directives that have to be complied with. Required are rules and directives that have to be complied with unless there is a deviation. Advisory are less formal and are more good practice rules. So what is a deviation? Normally, a MISRA-C rule is written this way. So they explain an issue, a problem, and then they explain also how to address it by writing safe software. A deviation could be something like an explanation on why on your software the problem cannot occur due to the nature of the software, or an explanation on why you use a different solution in your software because maybe due to the specific details, there is a better solution. But they are not common, but most projects doing safety, they have at least one or two. Because rules and directives are so many, it's difficult to analyze them by hand or just with your own pair of eyes. And that's why most projects use a static code analyzer. It's very important to integrate into your own CI loop and your own build and test and commit infrastructure. In Xen, we have already run a study on feasibility of doing MISRA-C compliance. The latest one was done by Resiltech, and the result is that it's definitely feasible. And if you look at the diagrams below, all the top violations, actually, the 4 or 5 top violations, are all false positives. So if you take those out, the remaining violations are actually not that many. So it's not that far from MISRA-C compatibility already, the code base. So what we are doing now is to look at the set of rules and directives that make sense for Xen, and for each of them, figure out what is the best possible way to check them automatically using a MISRA-C checker. It could be one MISRA-C checker or the other, or it could even be GCC. And most importantly, we are looking at integrating these MISRA-C checkers into the Xen project processes so that they run automatically before commit, ideally as part of our existing GitLab CI infrastructure. I wanted to show you a couple of examples to give you an idea on what the MISRA-C rules look like. On the example, you see one rule and an example that says you basically need to have brackets around single line statements in your if and else statements. And the reason is, if you look at the example, flag 1 and flag 2, action 1 and action 2 there, is that it's confusing. If you go back to the slides, so the real problem is sometimes without brackets, indentation can actually hide bugs. It's very easy to miss. So MISRA-C is telling us to always have brackets around single line statements, which is a good suggestion. Now in Xen, we have an existing code base, and we have quite a few examples of single line statement without brackets. So one option is to add the bracket. Maybe another option to explore is to use GCC. Now, a modern version of GCC can actually check for these misleading situations with the capital W misleading indentation warning. So that might actually address exactly the situation MISRA-C is worried about. A different example is the one we see here in the browser, is about ID length. So older compilers will truncate IDs, variable names or function names, and what will end up is you will end up calling the wrong function or using the wrong variable by mistake. So obviously this is pretty bad. So this is definitely a serious issue. So one way, going back to the slides, to address this is to mandate C99 compliance. C99 mandates that the compiler needs to support at least 31 characters to be significant. So if you use a C99 compiler and all your ID are not longer than 31 characters, you are good.
A few words about certifiable Xen configurations. Of course, Xen itself relies on some other tools beyond Xen. Traditionally, when Xen boots, it has a domain 0 that boots other domains, and DOM0 is built on Linux kernel. It contains all of the hardware and par-virtualized backends, and other domains use these backends to talk to the hardware driver. So basically, first of all, it's very hard to certify, if possible at all, because DOM0 is a single point of failure for both hardware, and Linux itself is, the kernel itself is pretty hard to certify. Again, if possible. So with that, one of the approaches to solve that is to put RTOS into the domain 0, okay, like so-called thin domain 0, and remove all of the hardware except probably some fools related to other domains. So when domains are crashing or restarting or whatsoever, they do not break each other. And DOM0 is very thin. It has potentially can have a certifiable real-time operating system managing everything else. So it's like one approach.
Another approach is to use DOM0less. DOM0less was created to shorten boot times. And the idea is to load all VMs, more than one VM at least, at boot time directly from the bootloader, and then to boot them in parallel. That means other domains like DOMU1 and 2 in the picture don't actually need DOM0 to start at all. So DOM0 is optional. But if it's optional, you maybe take it away. So no DOM0 means there is no DOM0 to safety certify. So also born for speeding up the boot time and doing parallel boot is actually a technique that can be used to get rid of DOM0.
Yeah. So another thing is actually determinism. In Xen, there's, at least on ARM, that's not true for x86, but at least in Xen on ARM, there are some hypercalls that are very long running, like for memory partitioning, for example. Latency can be up to 2 milliseconds because hypercalls are non-interruptible. And we did a POC using Zephyr with a very, very basic real-time scheduler configuration that's publicly available on mailing list. And with the implementing preemption, we've managed to get the 600 nanoseconds that on Renesas R-Card platform, 600 nanoseconds deviation and mean interrupt time up to 8 microseconds. So that's just the research that we've done. So in future, what we need to do is work on latency of the hypercalls, probably by introducing preemption for generic hypercalls or moving them into separate VM that will take care of the Xen's internal housekeeping.
Another source of potential interference for interrupt latency and real-time workloads is a shared L2 cache. So what happens is, due to the shared L2 cache, memory accesses can be a lot slower than usual, and even causing missed deadline for your real-time application. And that solution is cache coloring that, thanks to a smart allocation technique of memory in the hypervisor, you end up splitting the L2 cache into different subsets and giving a different subset of cache line to different VMs. That way, there can be no cache interference because there are no shared cache lines anymore. And the result is you have a lot lower RQ latency. More importantly, you have a lot more deterministic RQ latency, very little variations in times, and also a lot more deterministic execution times in general. And this is the end of our presentation. So thank you for attending, and let us know if you have any questions.
So Stefano, there was one question related to the tools we are currently using for mischecking.
I see. Do the compiler used to, in the project, also have to be safety certified?
I answered to that. In fact, they do not always need. That depends on the certification level and standard that you want to use. But in the highest level, yes, you would need a certified compiler. But right now, we are doing some tests with ARM certified compiler, for example.
ARM is a certified compiler based on Clang, and we do support compiling that. It's not yet upstreamed, but it is possible. There are some tweaks needed.
Yeah, but we are working on it.
In terms of MISRA-C checkers, there is a number that we are looking at. So there are a number of, we are collaborating with some of these companies. Among the proprietaries, there are at least half a dozen that we regularly check. There are also a couple that are open source, like the CPP check is an open source checker. And GCC itself has a lot of check nowadays that can be used for some of the rules. Also, it's not obviously a
regarding the Doxygen, so we are working on this with Zephyr project. There is nothing upstream yet. There should be some things coming in the next month. But yeah, we have some proof of concept, and the Zephyr project has some evolved proof of concept to link tests to requirements.
I can address the topic of RTDS. We actually, the test that we are doing on preemption and everything, that is based on using RTDS scheduler. It is marked as experimental in the code base indeed, but just polishing that and ensuring proper time accounting and eliminating all of the gaps, like I mentioned with the hypercalls, would go into like supported for the RTDS as well. So yeah, that's being worked on. And yeah, to your point, we actually targeting mixed criticality systems. Exactly, that's
right.
Why we need Xen.
Yeah.
Yeah, I think we are out of time.
Yeah.
We'd like to thank our presenters, especially for their time. I'm sure they would be available to continue answering any questions in the chat for a few minutes. And those of you who participated and asked questions, thank you very much. Thanks all.
Thank you.
Bye-bye.
Yeah.